with crib. So this video will focus on just doing straightforward conversions using enthalpy values as well as using your Q equals mc delta T equation. 35. The overall reaction in a commercial heat pack can be represented as 4 moles of iron plus 3 moles of O2 gas will yield 2 moles of Fe2O3 solid. Now, the enthalpy change for this reaction is 1652 kilojoules that will be released associated with this balanced chemical equation. It's really important that we associate this value with these moles. So that means for A, how much heat is released when 4 moles of iron is reacted with excess O2. If we're given 4 moles of iron, the proper conversion is that change in heat energy is associated with the 4 moles of iron, that 4 in the balanced chemical equation. Of course, 4 over 4 is 1, so this is 1652 kilojoules of heat energy that will be released. Notice how that changes if we have, in the next problem, how much heat is released when 1 mole of Fe2O3 is produced. So 1 mole of Fe2O3 is provided, and in the balanced chemical equation, 2 moles of Fe2O3 produced will be associated with that heat energy change. So that's negative 1652 kilojoules per 2 moles of Fe2O3 produced. Of course, then that would be half that. So, and then for the next one, we're just incorporating grams now. So you would have to convert the 1 gram of iron, 2 moles. Of course, that's substantially less than what we had here. So then once we do the conversion from moles of iron to kilojoules, we have a very, very small amount, right? And then for the final problem here, with 10 grams of iron and 2 grams of O2, you would need to determine the limiting reagent before you proceed, and then the conversion would be pretty much the same as C, meaning depending upon whichever is the limiting reagent. For 36, essentially you're doing the same type of problems, except for D, the total volume of hydrogen gas needed to fill the Hindenburg was 2 times 10 to the 8th liters at 1 atm and 25 degrees Celsius. Of course, they're giving you temperature, pressure, and volume. The missing variable here is moles, and you can of course use the ideal gas law to find the moles of hydrogen gas. Once you find the moles of hydrogen gas, you know that 572 kilojoules will be released for every 2 moles of hydrogen reacted. So then you would just need to do that conversion after finding the moles of hydrogen. Finally, we have a problem working with Q equals mc delta T. So they provide the specific heat capacity of silver right there, and they ask you to calculate the energy required to raise the temperature of 150 grams of silver from 273 Kelvin to 298 Kelvin. So here I have the mass, 150 grams. I have the heat capacity of the silver, and notice I have 0.24 joules per Celsius gram, and that is the same as per Kelvin gram. That's because although Celsius and Kelvin are in different scales, the change, the value of the Celsius degree and the value of Kelvin is actually exactly the same, right? That's why the conversion is we just add 273 to the degree Celsius in order to convert to Kelvin. That's because the actual units are equivalent to each other. So that's why here it doesn't matter what change. I don't need to convert this to Celsius to find that change in units is all that I need, right? For the change in temperature, the change in units that's exactly what I need in order to solve this problem. So of course, then this is 0.24 joules per Kelvin gram, and I can find the change in temperature here, and all I have to do is now simplify this. For B, they ask to calculate the energy required to raise the temperature of 1 mole of silver by 1 degree Celsius, called the molar heat capacity. So not the specific heat capacity, but the molar heat capacity. And all you're doing there is converting this specific heat capacity in per gram to per mole. And so you're just using the molar mass to do that. Finally, it takes 1.25 kilojoules of energy to heat a sample of pure silver from 12 degrees Celsius to 15.2 degrees Celsius. Calculate the mass of the sample of silver. Of course, we are just rearranging to solve for mass. So here I divided both sides by C and delta T. And so mass is equal to Q over C delta T. And substituting in our values, making sure that we're converting to joules here so that the joule unit cancels out, we'll be able to solve for grams quite easily. Till next time,